Hi everyone, welcome to this video where I'm going to discuss about the third method for error detection, which is your checksum. So in my previous videos, I demonstrated how the error detection schemes such as your vertical redundancy check, longitudinal redundancy check, two-dimensional parity, cyclic redundancy check are implemented. So in this video, let us discuss about checksum method. So checksum method is one of the oldest error detection techniques that is in use. It is actually used in the upper layer protocols, including the TCP, UDP, and IP. It is an error detection scheme. This scheme involves breaking up of your message into, let us say that K sections, each section containing the exact number of bits. So here, the data is divided into K segments, each of N bits. At the sender's end, the segments are added using one's complement arithmetic to get the sum. And towards the end, this sum is actually complemented to get the checksum. The checksum segment is sent along with the data segments. Now, if to understand this better, let us say that I have a data which is maybe 32 bits long. Let me assume that my data is 32 bits long. Now, if I want to use, I can go for either a 4-bit checksum or an 8-bit checksum or a 16-bit checksum. If I decided to use a 4-bit checksum, then I have to break this message into how many blocks? 8 blocks, and each block containing 4 bits. Now, if I wanted to use a, let us say that 8-bit checksum now, if I wanted to use an 8-bit checksum, then the same data block of 32 bits is now divided into 4 blocks, each block consisting of 8 bits. If I wanted to use a 16-bit checksum, then this block is actually divided into 2 blocks, each block consisting of 16 bits. So here K is the number of blocks that your message is actually divided into, and N is number of bits in each block. So what do you do? If I am going to, let me assume that if I'm going to take an 8-bit checksum for my data of 32 bits. So what do? I get 4 blocks, section 1, section 2, so on until this. These are 4 blocks here. I add all the 4 blocks together, and towards the end, I will get the sum. The sum will be also 8 bits only. And when I complement this sum, I get something called as a checksum. So this checksum will also contain the same number of bits which you created. So if I'm using an 8-bit checksum, I will get 8 bits here. If I'm using a 4-bit checksum, I will get 4 bits here. This checksum is now appended to your original data. So in my example, if my data is 32 bits, and if I'm using an 8-bit checksum, I will be adding the last 8 bits which I received after complementing the sum that I got by adding my 4 parts of the data or 4 blocks of my data. So this entire thing will be sent to the receiver. The receiver knows how many bits of checksum you're using. So what he will do upon receiving the 40 bits of data, what he will be doing is he will break this up into 5 blocks, including the checksum block as well. And he will simply add all the blocks together. And once he gets the sum, usually this sum will be all ones. When you do the complement, you should get all zeros. That means 8 zeros. If the result is 0, then the receiver accepts the data. Then it assumes that the data has been received without any transmission errors, and it passes it on to the upper layers. But if this complement is not 0, if something else comes in, then it will assume that there are some transmission errors that has happened during data transmission, and it will reject the data. So this is the whole concept of checksum. Whichever message that you have, you take it, you break it up into different segments. Each segment should consist of the same number of bits, and you add all the segments. Then you will get this sum. This sum should be complemented to get the checksum. This checksum now is appended to your original data and sent to the receiver. At the receiver's end, once again, the received message and the checksum block is divided into blocks, each block consisting of same n bits. And all these blocks are added together again. If your sum is all ones, then complementing it will get all zeros. If your resultant checksum is all zeros, then automatically the receiver assumes that there are no errors during transmission. If it is non-zero number, then the receiver assumes that there is an error in transmission. Remember that checksum is an error detection scheme. So it will only tell you whether an error has happened or not. That's all. It will not give you any details regarding whether, where, how many errors have happened, or in which bit position the error has happened. No such thing happens here, because this is an error detection scheme. So that is what I have written here. At the receiver's end, all the received segments are added using 1's complement arithmetic to get the sum. The sum is again complemented. If the result is 0, the received data is accepted, otherwise discarded. So what do you mean by discarded? That means the sender has to retransmit the data again. Okay, because this is an error detection scheme. Now let me take a numerical example and explain with a numerical example. Okay, so consider a block of 8 bits. So let me just count 1, 2, 3, 4, 5, 6, 7, 8. So these are 8 bits, 1100, 1010, which are to be transmitted using a 4-bit checksum. So illustrate how the transmission takes place. Because I was told to use a 4-bit checksum, now I'm going to divide this 8-bit block into 2 blocks. My k is 2 and n is 4. 2 into 4. 2 blocks of each 4 bits each. So the 2 blocks which I will be getting is 1100. And the second block I will be having is 1010. Okay. So what do you do, sir? You simply add it. So how do you add it? Just write like this. So 0 plus 0, 0. 0 plus 1, 1. 1 plus 0. I just wrote them in the form of a table for better clarity of understanding. So 1 plus 0, 1. 1 plus 1, 0, and a carry 1. Because I have to get the checksum again as a 4 bits only, what I will do is I will add this carry to my least significant bit. So this is what I do. I put this one here, and now I'll get 0. This 0 plus 1 is 1, 1, 1, 0. So this is my sum, which I got by adding my data blocks. And this sum should be complemented, right? Complemented to get the checksum. So this checksum is obtained after complementing this. So how do I complement? If it is a 0, simply put a 1 there. If it is a 1, simply write a 0. If you write a 1, simply write a 0. So this is your checksum. This is my checksum that I got. Okay. Now the data that you are going to send to the receiver will be what? This 8 bits plus your 4 bits of the checksum. So if you see here, these are the first 4 bits. These are the second 4 bits, and the last 4 bits correspond to the checksum that you just calculated. This data is sent to the receiver. Please remember that most of the students do make a mistake by not doing this step, by forgetting this step. They'll simply compute the sum of all given data blocks and they will just add it to the original data. But please remember, unless until you calculate the complement to get the checksum, this particular method is invalid. It will not do error detection. So this data is actually transmitted to the receiver. So what happens to the receiver side, or what happens at the receiver side once the receiver gets this data? It will simply add all the data blocks again. So 1100, 1010, 1000. So these are the 3 data blocks that the receiver received, that the receiver got. So add it. 0 plus 0, 0, 0. So 0 plus 1, 1. 1 plus 0, 1. 1 plus 0, 1. 1 plus 0, 1. So 1 plus 1 is 0 with a carry 1. 0 plus 1 is 1. Okay, there is still a carry 1 here. I told you, whichever carry is left you got here, you simply add it towards the end. So if you add it a 1, 1, 1, 1. Once again, this is your sum. And once you complement this, you get your checksum, which is all zeros. So once you get all zeros, it will automatically means that the receiver has received the data without any errors. So once the receiver adds all the received blocks of data, it computes the checksum. The result must be all zeros. If that is the case, the receiver assumes there are no transmission errors and the data is accepted. But if it is not, if for some purpose, if you do not get all zeros here, if any non-zero value is obtained after calculating the checksum, the transmission is assumed to contain errors and it is discarded. So this is how you calculate checksum. It's a very easy method. Please remember that if you are given data and if you are not mentioned how many bits of checksum to use, you are free to use your own value. You can either go for a 4-bit checksum, or you can either go for an 8-bit checksum, or either if you can go for an 16-bit checksum also. It's up to you. You have to break the given data into equal sized blocks and add all the blocks. You get the sum, and then you perform the complement to get the checksum. You will get the value. That value should be appended to the original data, and this original data should be transmitted to the receiver. So this is the concept of checksum. Let me show you another example. Now, for a pattern of, I'm given a pattern 1, 2, 3, 4, 5, 6, 7, 8. This is an 8-bit checksum I'm using here. For a pattern of this, find out whether any transmission errors have occurred or not, which means that this is the data which the receiver has received. The receiver has received this data. Okay. And we know that I'm using an 8-bit checksum here. So what does the receiver do? It will simply add all the blocks. Now I have written it down so that it is easy for calculation. 1, 0, 1, 0, 1, 0, 0, 1. Similarly, 0, 0, 1, 1, 1, 0, 0, 1. And the third block is 0, 0, 0, 1, 1, 1, 0, 1. So let me do the calculation. So 1 plus 1 is 0, carry 1, and 0 plus 1 is 1. So it is all zeros, 1 here. 0 plus 0, 0, 0 plus 1 is 1. 1 plus 1 is 0 with a carry 1, and 0 plus 1 is 1. So once again, 1 plus 1 is 0 with a carry 1, 0 plus 1 is 1. So 1 plus 1 0 with a carry 1, 0 plus 1 is 1. So 0 plus 0, 0, 0 plus 0, 0 is a carry 1 here. So 1, 1. So this is my sum. And if I complement it, what do I get? I get all zeros, right? So which means that this particular transmission does not have any errors. Does not have any errors, because the resultant checksum is all zeros. So before we close checksum, let me do a quick comparison with the other error detection scheme that is used widely today, which is your CRC, cyclic redundancy check. So CRC is more thorough as opposed to checksum in checking for errors and reporting. Okay, and the next thing is checksum is the older of the two programs. Checksum is the error detection scheme that is implemented at TCP or transport layer, the two protocols of TCP, UDP, and even in the IP also at network layer. The third one is CRC has a more complex computation as opposed to checksum. Checksum simply involves adding all the data blocks and then complementing the sum. But CRC, because it uses cyclic codes, you do polynomial arithmetic division. Okay, checksum mainly detects single bit changes in data, while CRC can check and detect even double-digit errors also. Whereas CRC can detect more errors than checksum due to its more complex function. So this is how you actually divide or you compare CRC and checksum. These are the two prominent error detection schemes that are being used today. So checksum is quite easy. You simply divide the data into blocks and then calculate the sum, complement it to get the checksum. We'll do more practical examples of checksum in the next videos. So till then, thank you and take care.